Okay, we have been discussing about attitude dynamics. So, in that context we are working out the moment of inertia. So, we are looking into the principal moment of inertia thing. So, we were given that the moment of inertia matrix, this is I 11, I 12, this was the moment of inertia matrix, and if the diagonalization is done, okay, so the off diagonal terms then becomes 0, off diagonal terms will be becoming 0, and therefore, we get the we get only diagonal elements. So, these diagonal elements are nothing but the principal moment of inertia I 1, I 2 and I 3, these are the principal moment of inertia. So, in this context we took an example of a cuboid. Okay, so, we had a cube of each of the side of the cube is A, and we assumed this mass to be m. So, ultimately what we got last time, that our inertia matrix we put in the format of two by 3 m a square minus m a square by 4 minus m a square by 4. Similarly, other terms here, because it is a real symmetric matrix. And therefore, we wanted to find out the principal moment of inertia from this place. So, we wrote the whole thing as I minus, say, we can put here some other subscript to indicate how does it differ from the other representation. So, in that context we have used notation. Okay, first of all we took out the m a square outside, and thereafter we kept the numerical terms inside only, and we said that the if we try to find out the moment of inertia. So, the finally whatever the numerical terms comes in the diagonal elements. So, those will get multiplied by m a square. So, while working in that terms, so we had the moment of inertia matrix, which we suppose we write it as I prime, not as I, because I most often while writing the matrix working in the terms of matrix notation. So, we indicate I is the identity matrix, or maybe we can keep here I g. So, therefore, I g was written as 2 by 3 minus 1 by 4 minus 1 by 4 2 by 3 minus 1 by 4 2 by 3. Okay, and for finding out the principal moment of inertia term. So, we have to write it in this way, and determinant of this is to be equated with 0, okay, where this is the identity matrix of 3 by 3 size, identity matrix, and this is what the we call as the eigenvalue. Now, in solving this, the whole thing got reduced into the format 2 by 3 minus lambda. So, determinant of 2 by 3 minus lambda minus 1 by 4 minus 1 by 4 minus 1 by 4 minus lambda, this should be equal to 0, and this term we wrote as alpha and this term we wrote as beta. So, ultimately the polynomial that we got. So, it was written as, so the whole thing we wrote this as this diagonal terms as the alpha and this off diagonal terms as beta. Okay. So, our equation got reduced into the format alpha minus beta, alpha plus beta times alpha minus 2 beta square equal to 0. So, this implied that alpha equal to beta, this was one of the solution. Okay. So, other two we get from this part. So, this is alpha square plus alpha beta minus 2 beta square equal to 0, and this implies alpha equal to beta, one solution, another solution is minus 2 beta. So, what we are getting that this alpha and beta, there are two repeated roots, two repeated roots. So, two principal moment of inertia they are basically equal. Okay. So, alpha already we know that alpha equal to, we have written as two by 3 minus lambda, and beta we have written as minus 1 by 4. So, alpha equal to, and so these two imply that 2 by 3 minus lambda equal to minus 1 by 4 and lambda equal to 2 by 3 minus plus 1 by 4. So, this we get as 11 by 12. Okay. So, finally, this lambda we need to multiply by m a square to get I 1. So, I 1 becomes 11 by 12 m a square. Okay. Similarly, I 2 will be equal to 11 by 12 m a square, and I 3 now we have to calculate. So, for calculating I 3 we have to write alpha is equal to minus 2 beta, which is this part we are using now. Okay. So, minus 2 beta minus 2 times minus 1 by 4, and obviously, alpha on this side we have 2 by 3 minus lambda. So, this becomes 1 by 2, and this implies lambda is equal to so 1 by 6. So, I 3 we get from there. So, I 3 will be equal to 1 by 6 m a square. Okay. So, these are the three principal moment of inertia that we have just now worked out. So, I 1 we are getting as 11 by 12 m a square, I 2 as now. If we assume m to be 1 unit and a to be 1 unit. Okay. So, it may be either you can consider in CGS unit or SI unit. So, I am not naming it either the m as kg and a as meter, or maybe gram and centimeter. So, this generalized notation I am using here. So, m is equal to 1 unit, a is equal to 1 unit here. So, therefore, I 1 will be 11 by 12, I 2 will be 11 by 12, and I 3 will be equal to 1 by 6. So, this is your, all these are the three principal moment of inertia. Okay. Once we have done this, so next our objective will be to find out their corresponding direction. So, we know already that we have to solve for m a square now it has got reduced equal to 1 because of one unit choosing a as 1 unit and m as 1 unit. So, therefore, we can write the equation as 2 by 3 minus lambda and 2 by 3 minus lambda, 2 by 3 minus lambda, here minus 1 by 4 minus 1 by 4 minus 1 by 4, okay. And let us say alpha 1, alpha 2 or alpha 1, beta 1 and gamma 1, these are the 3 eigenvectors corresponding to lambda equal to, the first one we can take as first one we can take as 1 by 6. Okay. So, if we take this value to be 1 by 6 and then we need to solve. Okay. So, basically your inertia matrix is now looking as this I g, this is looking as 1 by 6, 11 by 12, 11 by 12. Okay. Off diagonal terms are 0. So, we are choosing the original equation where we try to find out find out these eigenvalues. So, once eigenvalues are determined, now we are set for finding out the eigenvectors which are given by alpha 1, beta 1, gamma 1. This is one eigenvector whose components alpha 1, beta 1, gamma 1 are to be determined. So, for doing this, first you need to insert lambda is equal to 1 by 6 here in this place, and then you need to solve, and last time I explained how to do that. You can choose one. Okay. Here you have two independent equations. See, this value will turn out, this matrix will turn out to be singular once you put 1 by 6 into this, you can check it. Okay. So, therefore, it indicates that only two independent equation you will get. So, for doing this, what you need to do, you assume one and find other two, okay, and then solve for this eigenvector. So, similarly, next time you take this one, and in that case, because this is the repeated eigenvalue. So, you will get only one independent equation. For this case, you will get two independent equation, while for these are the two repeated roots. So, you will get only one independent equation, and then you can find still you can find two independent vectors, eigenvectors. Okay. So, even if you have the repeated eigen values, so you can have two independent eigenvectors, but if you have the independent but the converse is basically not true. Okay. So, here what we are going to do, that instead of working out the whole thing, because it is going to take time, our time for this particular part is limited. So, I will suggest you look into the web lecture, and for the time being you can use the command in the MATLAB, say v comma d, okay, inside the large bracket, and this you can write as eigen, and the eigenvalue matrix you can write here as I g. So, this will list you the V matrix as minus 0.5999774 and this is minus 0.15 minus 0.6172 0.5345. Okay. So, this vector this is one vector, this is another eigenvector, this is another eigenvector. So, this eigenvector it corresponds to your eigenvalue of lambda is equal to 1 by 6, while these two they correspond to lambda is equal to 11 by 2, 11 by 12. And the MATLAB, the output it will give the another output, that will be d, and you will find d to be 1 by 6. So, instead of 1 by 6 it will list it as 0.1667, the off diagonal terms being 0. Okay, this is 3 into 3 matrix. So, you get the eigenvalues simultaneously by using this command. You will get the eigenvalues and also the eigenvectors. Now, as we listed in the properties of the real symmetric matrix, we stated that a full set of 3 orthonormal eigenvectors will be available. So, a real symmetric matrix will have a property which states that it will have a full set of 3 orthonormal eigenvectors. So, this implies that the eigenvectors that we are getting here, this is, let us say this is nu 1, this is nu 2 and this is nu 3. So, here nu 1, nu 2, nu 3, these are the eigenvectors. Now, full set of orthonormal eigenvectors implies that nu 1 transpose nu 2, this will be equal to 0. Similarly, nu 1 transpose nu 3 will be equal to 0 and nu 2 transpose nu 3 will also be equal to 0. So, this is the orthonormality, and orthonormal, why this is orthonormal, because you can check this is the B 1 transpose V 1, this you will find equal to 1. Similarly, you will find V 2 transpose V 2, this is equal to 1, okay, and V 3 transpose V 3, this is also equal to 1. So, this is normalized eigenvectors. So, as we stated that here we can get a number of solution for alpha, beta 1, gamma 1, but in the normalized form it will represent a unique direction, okay, and that is the direction of the principal eigenvalue, and which is the principal moment of inertia in our case. So, okay, so whatever we are getting here, you look into this eigenvector. So, this is corresponding to lambda is equal to 1 by 6. So, this is the principal moment of inertia. So, I 1 is equal to 1 by 6 units. So, this is our first principal moment of inertia, and the corresponding eigenvector is indicated here. And if you look from say this is E 1, E 2 and E 3 vectors. So, principal moment of inertia direction, this is all with a negative sign, here it is all shown with a negative sign. So, we will make it here the this part. So, these are the positive directions. Okay. All of E 1, E 2, E 3 positive, it will go in this. You can assume that there is a vector which is unit in magnitude. Okay. So, unit magnitude vector will say this vector is unit in magnitude, and the angle from here to here, this is say alpha 1, this angle sorry, this angle is alpha 1 and this is beta 1, this is making with E 3. So, we have written this as the gamma 1 in the last lecture, and this angle from with E 2, this is beta 1. So, alpha 1, beta 1, gamma 1, and this all three angles will be equal to they are all equal. So, now we do not have to take in this direction, but rather it is a all the signs are negative, basically these are all cosines. Okay. Alpha 1, beta 1, gamma 1, whatever we are getting, they are the all cosines value. So, working out all of them, you have to just take in the negative direction. So, what is the part minus 0.577. So, you take along the negative x x minus 0.577 along the negative y x, this is the negative y x. So, you take minus 0.577 and along the negative z x. So, you will get just a vector opposite to this, okay, and this is the principal direction which is being shown, and now you can see the angle that is now we can cut this. Okay. So, your angles are now from here to here, this is your alpha 1. So, this is your direction E 1. So, with E 1 we are measuring alpha 1, and with E 2 direction, this is E 2 direction. So, with respect to E 2 we are measuring the angle, then this angle is your beta 1, and from here we are measuring. So, this angle is your gamma 1. So, that is how you locate the So, these are all here one thing I would like to say that these are all cosine values, means alpha 1 we have written. So, instead of writing alpha 1 we could have written here as cosine value as cos alpha 1, okay, as cos beta 4 and cos gamma 1, beta 1 and cos gamma 1. So, these are whatever you are getting, these are all the cosine values. So, if you write cos inverse minus 0.5774. So, this gives you the value here alpha 1, and similarly beta 1 you can get as cos inverse minus 0.5774 and so on. Gamma 1 also you can write as cos inverse minus 0.5774. So, so here you remember these are the cosine, these are along with the cosine. Actually, I wanted to show you this is just a vector. So, this vector corresponds to this cosine value, last time I have stated. So, here I missed it. So, now this part is finished. Okay. You can similarly in the same way you can take the next vector, which is now okay, here 0.1543 minus 0.1543, 0.7715 minus 0.6172, and this corresponds to lambda is equal to 11 by 2. In the same way you can find out these angles. So, take care of that these are all negative. So, they are lying in the, if it is negative means lying in the second quadrant, and means it is a proper sign value actually you should always take while resolving it. So, you take all the proper values and work it out. Another way of doing the same thing, because you can see that these are the cosine magnitudes, that is cos alpha 1 equal to 0.5774. If we are writing like this, means if I have a unit vector here, if this is a unit vector. So, 1 times cos alpha 1, this will give you 0.5774. Okay. And this is basically the intercept, its intercept on the x axis. So, in this case it will come out to be negative from here to here, and its value will be minus 0.5774. Okay. So, basically all these quantities whatever you are getting here, these are the normalized values, and therefore, they are indicating the intercepts on the x, y and z axis. So, similarly, these are the intercepts on the x, y and z axis. So, if you use the proper proper placement of all these points, so you will get the location of the principal inertia direction and principal inertia magnitude we have already get in this units, in generalized units, lambda is equal to 1 by 6, 11 by 12 and 11 by 12. Okay. Okay, so, this completes our discussion about the moment of inertia. Okay. Now, if you look for the equation that we have started with, H equal to R r dot and this we integrated over the whole body. So, this gives us the angular momentum vector, but we did not expand this equation completely and got it in a real form, in which we have written the, we try to work out the moment of inertia of this cuboid. So, this time I am going to finish this part. So, say r equal to r, or either we choose perhaps in the last lecture as rho. So, either you can use the r or rho, where we are considering this body, any point p is there, and this is the vector r from here to here, and omega is the angular momentum vector, angular speed. This is basically the angular velocity vector, and this we are taking as the center of mass. And this was our principal inertial reference frame, and we had another frame which was fixed in this body at the center of mass. This was E 1, E 2 and E 3. So, these are the body x, and unit vectors in this direction, accordingly we choose E 1 cap, E 2 cap in E 3 cap. So, this was E 2 cap, E 1 cap unit vectors, and E 3 cap in this direction. So, r we can write as either as in the notation of x E 1 cap, y E 2 cap and z E 3 cap. We are representing this vector r in the body reference frame. Okay, what will be the components of this is written here, or either the same thing we can write as r 1 E 1 cap plus r 2 E 2 cap and r 3 E 3 cap. Both are them are same, it is nothing different, only thing notations we have changed. Okay. So, now taking up, considering that r we are writing as x E 1 cap plus y E 2 cap plus z E 3 cap. So, the each vector can be written as, first of all we will work out the inside material of the inside the integrand. This integrand we first of all we will work out, and then we will do the integration part. So, let us do that part. R dot r, this is x E 1 cap plus y E 2 cap z E 3 cap dot y E 2 cap plus z E 3 cap. Okay, take the dot product. So, this gets into this form. Similarly, you have r dot omega. So, r dot omega E 1 y E 2 z E 3 cap dot omega 1 E 1 cap, or omega 1, instead of writing omega 1 I can write also as omega x to indicate. So, basically if you use this as small x, this as a small x, small y, and this as a small z. So, we can use this notation omega x, omega y, and unit vectors are still we can keep the same notation. Quite often the unit vectors are in the x direction I indicated like x cap, in the y direction as y cap, in the z direction as z cap. So, what I was following with E 1 cap, E 2 cap, E 3 cap, these are the generalized notation rather than writing in terms of x, y and z. So, they represent any three orthogonal direction. So, anyway, whichever way you write, it does not matter, the result will be same. So, this is omega z E 3 cap. So, this will give you x times omega x plus omega y times y and plus omega z times z. Okay, finally, r dot r times omega, this will be x square plus y square plus z square times omega is omega x E 1 cap, omega y E 2 cap and omega z E 3 cap. Similarly, we have r dot omega times r, this is x omega x plus omega y times y or y times omega y and z times omega z times x E 1 cap plus y E 2 cap plus z E 3 cap. Okay. And then we need to subtract them. So, r dot r times omega minus r, this quantity will be equal to x square plus y square plus z square E 2 cap plus omega z E 3 cap minus z E 3 cap, and then this can be simplified. Okay. So, if you simplify them this equation, so this will turn out to be y square plus z square. You collect the terms similar terms, means you have to collect all the terms corresponding to E 1 cap and similarly corresponding to E 2 cap from both these terms and write together. So, this will result in omega x y square plus z square omega x minus x y times omega y E 2 cap, and the third term we write on the next page. The third term will be, so y z x square plus z y square plus z square we have taken x square plus z square. So, this is basically a cyclic thing, x times z. So, it is easy doing from here. What we have done, E 1 cap term we have to take out. So, you multiply this whole thing with omega x. So, E 1 cap will come from this place, and this term, the whole thing multiplied by this x, and it will come on this side. So, you will see that here x square E 1 term is appearing times omega x, and also here you have the term omega x times x square. So, these two terms cancel out, okay, and you get y square plus z square, which was appearing here as the first term, okay, multiplied by omega x, and rest other terms which come from this place. So, y omega y, this multiplied by x. So, x y times omega y. So, x y times omega y with a minus sign which is appearing here, okay, and similarly x z times omega z. So, x z times omega z which is appearing here. So, we are just collecting the terms together and writing here in this place. Okay, so, once we have written this, so h can be written as inside the integration sign y square plus z square E 1 d m E 1 cap d m plus the last term we wrote as this is the last term. So, x square plus y square omega z minus x z omega x minus y z omega y E 3 cap d m. Now, the quantities which are present here, so you can easily identify them. So, you can write I x x equal to y square plus z square d m integration over the whole body. Similarly, you can write. So, this is the first term we have picked up. This is the second term. So, this is x square plus z square. So, this is the term which indicates I y y. So, x square plus z square times d m. Similarly, I z z, this is this term. Others you can identify as the cross product of inertia. So, the other terms we will write as like the x y time d m, this will write as I x y, and similarly I x z we write as x z d m, and I y z we write as y z d m. So, this equation that we have written from here to here, this will get reduced to h you can write as. So, omega if you are doing the integration over the body, not over the omega, you remember. Okay. So, this can be taken out. So, what we can write here I x x times omega x minus I x y times omega y minus I x z times omega z times E 1 cap plus again you have to take this term will be taking first I x y times omega x plus then this term we choose, and here we write as I y times omega y and then the last term here it is I y z. So, this with a negative sign times omega z E 2 cap, and similarly the third term we can write as I x z with a negative sign here omega x minus I y z times omega y and plus I z z times omega z E 3. So, we have just rearranged the terms which are present here and written it in this format. Okay, so, this is what appears in the vector notation. So, okay, so we have this 3615. So, each can be written as H 1 times E 1 plus H 2 times E 2 plus H 3 times E 3 cap, or either you can write this as H x, H y and H z. So, these are the three components of the angular momentum vector, and in matrix notation the same thing you can write as H x, H y, H z, or either in terms of H 1, H 2, H 3. This as omega x or omega 1, whichever you want to use. Okay. And put all the terms from here to here in this place. So, this will give you I x x minus I x y minus I x z. Here you get minus x I x y, I y y and minus I y z. Similarly, here you get minus I x z minus I y z and plus I z z. Okay. So, this is your inertia matrix. So, this is your inertia matrix I g times this is the omega vector, and this you can write as the angular momentum vector. So, in matrix notation, this is a very compact representation, and this is what we have written earlier. So, earlier without deriving this equation, we have used it to find out, just we wrote this as I 1 1 and then we worked out this as writing this as R 1 R 2 square plus R 3 square d m, and this we integrated and wrote as I 1 1. So, same notation you can do for all other things. So, what we see that whatever we used earlier, this can be derived in this way. Okay. So, you see that from this place your H x or either H 1 which you are writing, this is nothing but this particular quantity from here to here. So, this is your I x x omega x minus I x y omega y minus I x z omega z, and this you can also get from here if you do the matrix multiplication. So, this is 3 into 3 matrix and 3 into 1 vector. Okay, so, working out in this way, we have got I y times omega y minus I y z times omega z, and omega x minus I y z times omega z, and this is plus I z times omega z. Now, once we have done this, so our main objective is to find to compute the Euler equation, to find out how the Euler equation you might have heard earlier. So, if a torque is acting on the rigid body, okay, a rigid body is given, and if you apply torque to this, so what will be the change in the rotational rate of the body. So, we say we have the inertial axe here E 1, E 2 and E 3, and I have a body here in which a set of x E 1, E 2 and E 3 are fixed. This is the center of mass. Okay. So, if I apply a body, first of all you remember that we have got the moment of inertia, this angular momentum about this center of mass. This is our angular momentum vector, and this is the angular velocity vector. So, in general your angular velocity vector and the angular momentum vector, they are not in the same direction, which is evident from from this equation itself. You can see here your h vector is given by this, where the omega is getting multiplied, and thereafter you are writing, while your angular velocity vector is written differently. So, h vector you are writing as h 1 E 1 cap plus h 2 E 2 cap plus h 3 E 3 cap. Okay. While omega vector you can write as omega 1 times E 1 cap plus omega 2 times E 2 cap and omega 3 times E 3 cap, and where this h 1 and omega 1, they are not equal in general. So, therefore, this h and omega vector, they are not in the same direction. When they will coincide only if the rotational axis is also the principal axe. So, principal axe fundamentals we have already got, that if in this matrix, this is the inertia matrix, if this off diagonal terms, they all become 0, okay, leaving only the diagonal terms, then we call them as the principal direction. So, you given a, this is a real symmetric matrix. So, given any matrix, you can always reduce into a diagonal matrix, and you can make the off diagonal, that is you can make the off diagonal terms 0. Okay. So, in that condition, now you have this body, and then the principal x direction you can show as, say, let us say this is the I 1 direction, this is the I 2 direction, and this is the I 3 direction. So, until unless your rotation is along any of the principal axe. So, if this body is rotating about this principal axe, here this I 1 we have written. So, if it is rotating about this axe, so omega vector is coinciding with this, only then the angular momentum vector and the angular vector both will be same. So, here in general we write this as H, we are writing as I matrix and times okay. In this format, Obviously, this is not conducive for here this is the format what we have used here. So, in this format you can see that the off diagonal terms are present. So, obviously, you do not have the principal x consideration here. So, we need to reduce it first into that form. So, let us write this as h equal to h 1, h 2 and h 3, and we write this as I 1, I 1, I 2, I 3, rest other terms 0, and here we write as omega 1, omega 2, omega 3. So, still you can see that h vector you can write as I 1 times omega 1 E 1 cap, I 2 times omega 2 E 2 cap plus I 3 times E 3 omega 3 times E 3 cap, and from where we are taking this? We are taking from this place. This is what we are using here. Okay. This is finally what we used. Okay. This is your h 1 term, this term is your h 2 term, and this term is your h 3 term. So, if your off diagonal terms are 0 means this goes, this goes. So, only I x s times omega x. So, I x x instead of writing this we have written as the principal inertia as I 1, and this is omega x we have written as omega x we have written as omega 1. So, these two terms drop out leaving at E 1. The next term we have taken, this term will be 0 of diagonal term, this will be present. So, this we have written as I 2 times I and omega y 2 we have written as omega 2 times C 2. So, if you see this, while this is the angular momentum vector, and omega vector you can see we write as this we have written always in this format omega 3 3 cap. So, from here it is a very clear that the h vector and the omega vector they are not parallel. So, h vector and omega vector they are not parallel. Okay. For them to be parallel means the condition in which you can write h equal to omega, and let us say I define this as I 1 times omega 1, h is equal to I 1 times omega 1. So, what does it imply? If I try to write like this, if I can make omega 2 0, this becomes 0, this becomes 0. Okay. So, these two terms will vanish. What you get here? I 1 times omega 1 E 1. Okay. Similarly, here omega 2 is 0, omega 3 is 0. So, you can see that omega equal to omega times C 1. So, in that condition, these are the components here, and here this is the unit vector multiplied by. So, both are in the same direction. So, the angular momentum vector and the angular velocity vector they will get aligned, or they are in the same direction if and only if the rotation is along the principal x. So, here we can state angular velocity vector and angular momentum vector are in the same direction if rotation is about one of the principal x, otherwise not. Okay. So, we will conclude our discussion here. So, next time we can continue with this. So, next time we will develop the Euler's equation and also the kinetic energy of a rotating rigid body. So, these are the target for the next, and then we look into some small stability problem for a torque free rotation rotating rigid body, and that will conclude our discussion about this attitude dynamics. So, thank you very much.